Hello everyone, this is Zhihui Gao. I am glad to share our work, an audio frequency unfolding framework for ultra-low sampling rate sensors. This is a joint work by Zhihui Gao, Minxue Tang, Ang Li, and Yiran Chen at Duke University. There are 4 sections for today's presentation: background, framework design, evaluation, and conclusion. Given an analog acoustic signal, we can sample it with high sampling rate microphones, where we get good quality audio. However, sometimes the sampling rate of the microphones might be limited to a low level because of the low power consumption or limited storage and communication issues. Obviously, it is easy to downsampling a high sampling rate to a low sampling rate. On the other hand, is it possible to transfer a low sampling rate to a high sampling rate to improve the audio quality? Audio super resolution is an existing technology that improves the sampling rate. However, it is different from the audio frequency unfolding in our work. Now, let me introduce the difference between the audio super resolution and the audio frequency unfolding. We first examine the scenarios for audio super resolution. Suppose we have an analog signal whose spectrum is shown below. In audio super resolution, the signal is collected by a high sampling rate sensor. Being high means the sensor's Nyquist frequency is higher than all the peaks of the signal. Then the collected signal goes through a low-pass filter before downsampling. The high frequency peak is removed by the low-pass filter. As a result, the spectrum in the low frequency will not be impacted after downsampling. Finally, the audio super resolution is adopted. As the spectrum shows, the task of audio super resolution is to generate the high frequency peak. Then, we discuss audio frequency unfolding. We have the same analog signal as before. Different from the scenario of the audio super resolution, there is no high sampling rate sensor or loss pass filter. Instead, the signal is directly collected by a low sampling rate sensor. According to the theorem of frequency aliasing, the peak in high frequency will appear as an unexpected peak in the spectrum. Here, the task of audio frequency unfolding is not only to generate a high frequency peak, but also to remove those unexpected peaks. Next, I will introduce the details in the framework design. First, I will introduce the module of audio to spectrogram. Audio to spectrogram transfer the low sampling rate audio to a spectrogram by short-term Fourier transform. In this module, we develop an improved algorithm for pre-processing. The logarithmic spectrogram provides more details, especially in the high-frequency band. However, directly taking logarithm will amplify the noises around zeros. Thus, we add a small constant before taking the logarithm, which depresses these noises. The following module is a spectrogram unfolding. Spectrogram unfolding unfolds a low sampling rate spectrogram to a high sampling rate by a UNet-based deep learning model. In this module, we adopt UNet as the backbone of our model architecture, where there are downsampling blocks, residue blocks, and upsampling blocks. To improve the performance, we utilize a gated linear unit, or GLU, and instant normalization, or IN. These deep learning technologies are commonly used in time series-based model architectures. The core layer for upsampling is the pixel shuffle layer. Here, we develop a new pixel shuffle layer for audio frequency unfolding. When unfolding, the even number of the whole spectrograms are flipped around the frequency dimension. Such improvement is based on the truth that the odd number of the spectrums are unchanged, while the even number of the spectrums are flipped when the frequency aliasing occurs. The last module is the spectrogram to audio. Spectrogram to audio transfers the spectrogram to a high sampling rate audio using a fast Griffin-Lin algorithm. This is an existing algorithm that efficiently recovers the spectrogram to audio in the time domain. Also, a loss function module is developed to update the spectrogram unfolding module when training. The loss function examines the discrepancy between the original and the reconstructed audio to update the model. The training pipeline is shown below. When training, we produce the input audio by downsampling an original high sampling rate audio. This original audio can serve as a ground truth for the reconstructed audio. There are two parts in the loss function. We first introduce the reconstructed loss, which compares the spectrogram through a cyclic way. This is calculated by three steps: downsampling of the original audio, model inference, and downsampling of the reconstructed audio. The reconstructed loss compares the spectrogram of the original audio and the reconstructed audio for both high sampling rate and low sampling rate. Such a cyclic reconstructed loss alleviates the overfitting issue. We also exploit a perceptual loss to improve perceptual quality of the reconstructed audio. The perceptual loss compares the acoustic features extracted from the spectrograms. In our implementation, we extract filter banks as the acoustic features. This perceptual loss makes the reconstructed audio recognizable for human ears. This is a system overview of the 4 modules in our system. Then, let's see the performance of our audio frequency unfolding system in evaluation. The dataset we use is AudioMNIST. AudioMNIST contains 30,000 audio samples with 500 milliseconds each. They are spoken digits from 0 to 9 by speakers whose native languages are English, German, Chinese, and Spanish. We evaluate our system on the GPU Titan RTX with 24,000 megabytes. The inference time for each audio sample is 224 milliseconds, shorter than the audio length. This means our system can unfold the frequency in real time. Instead of utilizing the metrics in previous audio super-resolution works that compare the spectrogram's details, we focus on audio quality at a perceptual level. We adopt a state-of-the-art automatic speech recognition system, which achieves over 99% accuracy as the original audio. In our evaluation, we use a pre-trained automatic speech recognition system to recognize the reconstructed audio. Then, we check if the predictions are the same as the labels. In our default settings, the input sampling rate is 2 kHz and the output sampling rate is 16 kHz. We extract 4D features and no extra noises are added to the input audio. We first take a look at the spectrogram of the original, the input, and the reconstructed audio. Specifically, we select 3 representative digits, 1, 7, and 8. Compared to the original spectrogram, the reconstructed spectrograms are blurred at a high frequency band. Then, we examine the feature reconstruction under the same default settings. Compared to the spectrogram, the reconstructed features over time are more similar to the original features. This is because of the perceptual loss that minimizes the extracted features. Also, the similar reconstructed features make the reconstructed audio recognizable. We finally show the confusion matrix recognized by the automatic speech recognition system. Most of the digits can be correctly recognized with high accuracy. The overall recognition accuracy is 77.1%. We also evaluate system robustness against 2 factors. Note that the untested factors remain the same as the default setup. First, we examine different input sampling rate from 1 kHz to 16 kHz. The higher the input sampling rate is, the higher the accuracy it achieves. Then, we add different levels of noise to input audio. As long as the signal-to-noise ratio is no smaller than 10 decibels, the reconstructed audio can be recognized at a close accuracy to the default setup, where no extra noise is added. In the last section, I will summarize our work. In this paper, we present a frequency unfolding framework that reconstructs the audio collected by ultra-low sampling rate sensors. The proposed framework utilizes a U-Net-based model architecture and reconstructs the audio of better perceptual quality. We adopt the recognition accuracy of the automatic speech recognition system to evaluate reconstructed audio by our framework. Exhaustive experiments show the reconstructed audios from 2 kHz to 16 kHz can be recognized by the automatic speech recognition system at accuracy of 77.1%. Our work enriches the usage of the sensors with low sampling rates, moving one step closer to the real-life adoption of ultra-low power sensors. Thank you for your attention. If you have any questions, please let me know.